Morning, everyone. Morning, Azra. Morning, Kimmeline. Morning, Ryan. Morning, Hike. Morning, Kim. Morning, Ava. Morning, Jake. Morning, Downey. Hope you're all doing good. See, we're on period B today. Zooming in, taking a look at the agenda. But I already kind of told you what we were going to be doing today. Yesterday, we'll be doing DNA number 3, filling out box number 3. This is the last DNA for the week on a Wednesday. So on your sheet, remember, you can delete the 4th row. You don't need it. And then we'll go into just reviewing each of the applications for the GSA, the directions, and then give you time to work on phase 2. I mean, you should be working when I'm providing information, but unless you guys got a lot of questions, I'll just be answering questions in email remind, or I'll jump over to Miss Kildoff's group and help out there. And if you have questions, you can join that too. Alright? But again, I'm just going to be providing information on each app, and unless you have a lot of questions here, then the stream's probably going to be a little shorter than normal. Alright? Tomorrow we will review for the DNAC, we'll take the DNAC, and then we'll start phase 3. So it'll probably be a little longer, like normal. Hi, Charlie. DNA number 3. Again, we're looking at relationships amongst planets and their characteristics, because we can look at our solar system as a model for solar systems around the galaxy. What's a galaxy again? Galaxies are collections of stars, dust, and gas. Billions or trillions of stars depending on the size of the galaxy. Alright? So, what is the relationship between a planet's distance from the sun? So we're going to use AU, astronomical unit, the distance between the Earth and the sun. So how many AU versus the average day temperature? And then see the attached data table for the highlighted information. So you're answering in the third box this question. What's the relationship? And again, are there any outliers? Are there any exceptions to the rule? On Monday, we saw that Uranus and Saturn are exceptions to mass versus gravity because they're very, very low in density. They have so much mass, but they have an incredibly huge volume compared to that mass. They're very low in density, and their surface gravity is a little harder to really pinpoint. So they become outliers. Yesterday, we looked at distance versus rotation, or I'm sorry, mass versus rotation, not distance. And in mass versus rotation, all the planets except for Venus followed a negative relationship. Venus again has a very thick atmosphere, so it was causing it to drag on the planet itself when it rotates. So today, is there an outlier? Is there an exception to the rule? Distance from the sun. Earth is 1 AU. Mercury and Venus are less than 1 AU, so they're shorter than the distance from the sun to the Earth, which makes sense, right? So these are all in order based on AU because they're in order from the sun. So this is the only column that really puts these in order. Alright? Temperature is then right next to it, so easy to find. So you click that. So we analyze the data. I go to your sheet. Reminder that you can delete row 4. I would make a table again. 3 by 9. Put it in there. Rankings. And then today we would be doing distance in AU from shortest to from closest to furthest. and then average day temperature. I forgot if I gave it to you in degrees Fahrenheit or Celsius. Let me see. I gave it to you Celsius. That's just the average. We'll go from lowest to highest. Because we've been doing smallest to biggest number, smallest to biggest number, lowest to highest. Hi Charlie, hi Eric, hi Nikolai. So again, comparing distance and temperature. So ranking, distance, and AU close to far. Day temperature, low to high. Our 8 planets. Let's start taking a look at the data. So we're going to put them in order because Mercury is the closest. 0.39 AU, Venus 0.72, Earth, Mars, Jupiter's 5 times, a little over 5 times further from the Earth to the Sun. And then notice how, like I said, the outer solar system, the planets almost double in their distance from the Sun as you start working out. So Jupiter is 5 times greater distance the Sun to the Earth. Look at Saturn. It's almost 10. 5, 10. Uranus is close to 20 at 19. And then Neptune, not as far as it could be, but far at 30 AU. It's okay if I do the temp high to low. You kind of put yourself in a situation where you make yourself automatically have to have a negative relationship or no relationship because you don't leave the possibility that they can both increase. Jake. I think in the short term it's not going to hurt you, but I think in the long term it's better if you set it up this way so you see why. I don't want to tell you what the relationship's going to be, but why it's better to do it this way. It shows the distance. You're right. You do what you do what you're setting up. How does it hurt the further away? Because you're setting it up the same way for distance. You're still doing close to far, right? You flip the direction of your variable. So as you move further out, I'd have to do it. I have to see it. I can't picture it right now in my head. I just want to I want to move on to talking about GSA. So, distance from the sun in AU, average temperature sunlight side, degrees Celsius. I'm going to put them in order, and then I'm going to compare the temperature. So, I'm putting it in my chart. Mercury, Venus, Earth. Oops, a little off. Mars, Jupiter, Saturn, Uranus, Neptune. So quickly, took distance, put it in, went from closest to furthest, because the planets are already in closest to furthest order. We put them in order from the star, from the sun. Alright? Temperature. Low to highest. Obviously, negative 220. Is Neptune. After Neptune, a little warmer, so a little higher than negative 220 is negative 210, so Uranus. Negative 210, next lowest, we have the negative 100s. So we have Saturn, we have Jupiter. Obviously, we're going to go with Saturn at negative 180. Because negative 150 is greater than 180, right? You guys know your negative and positive integers. I was killed off. Because I... Stupid face in the way. There. After Jupiter, remember we have 20 and negative 20. Negative 20 is less than 20. So Mars, Earth. Everything has been a mirror flipped so far. And then the last two, Venus and Mercury. A little bit out of order. Mercury is a little less hot, with Venus being the hottest. So going back to my chart, we're going from coldest to warmest. We're going from closest to furthest. What you can determine, if we kind of connect the dots again, like we did yesterday. Oh, why is that black? Mercury. I'm going to skip Venus. Earth. Mars. Jupiter. Saturn. Uranus, and then at the end, Neptune. So they're perfectly flipped. When you have one variable do the opposite of the other, just like yesterday, we can say that this is a negative relationship. So what does that mean? Mercury being so close has a high temperature, if you follow that line. All right, Neptune being so far away has the lowest temperature. So as you increase in distance from the sun, the colder you get. Or maybe this is how Jake Rainey set up his chart. The closer you move in towards the sun, the warmer you become. And I think that relates pretty well to what we talked about in the beginning of the year. All right, this type of heat transfer is radiation. You're receiving more radiation the further into the solar system you go. You receive less radiation the further you go out of the solar system, which means less energy. Again, we're not talking about coldness, because cold isn't a thing. So, Venus. Venus is the hottest planet, but it's not the closest. Venus is once again an outlier. Why is Venus an outlier? Thanks, Miss Kilduff. Maddie Brown really likes it. And one of our resident experts on Venus, Kim, says a thick atmosphere acts as a greenhouse which heats the planet more. And there you go. Hike follows her up, says it's because of the thick atmosphere trapping sunlight. Yes. So it's like doing back at school the greenhouse warming lab, but instead of using a plastic bottle, you're using like what would be even better than the plastic? You know, probably like actual glass would probably be even better. Or a thicker plastic bottle. Something like the big 2-liter bottles, but on a smaller scale, right? So you're using a real thick plastic bottle, you'll trap more and more heat. All right? You'll stretch it, you'll redshift that light to infrared, you'll trap it and keep it inside, and it'll cause it to become very warm, right? So let's kind of write that out. Relationship is negative, okay? If distance is increasing, then temp decreases, right? If distance is decreasing, so you start going towards the sun, then temperature increases. So we're taking common sense, but we're just putting it into logic. We're breaking down why this happens. And this also helps you think about how to do a hypothesis, right? If distance increases, comma, then temperature decreases because there is less radiation from the sun. Right? If temperature decreases, then temperature will increase because there is more radiation from the sun. So again, using logic to explain something that's common sense. The closer you are to the fire, the warmer it's going to get. The further you are from the fire, the colder it's going to get. Negative relationships do the opposite. Same as yesterday, just different variables, right? The only one that was positive so far was mass and gravity. Okay? So what's the outlier? Venus is the only outlier. That kind of looks like a G. Venus is the only outlier, which means an exception to the rule. Because we'll just take right from the chat. It's thick atmosphere acts as a greenhouse and heats it even more. Thanks, Kim. Whoops. Want that to be black. There. Yeah, Venus again. Venus is the troublemaker in trying to analyze what's going on in the solar system. So, in black and in purple, I don't remember if I did Monday the same format. I'd have to double check my screenshot. But in black, you're going to have one question on the test, the quiz tomorrow. And then in purple, you're going to have a follow-up question. All right? So that's what I'm going to be doing in terms of the DNAC. Asking you about the relationship, asking you about the outlier. Okay? So no both. Monday was mass and surface gravity. Yesterday was mass and rotation. Today was distance and temperature. And again, we're using our solar system as an application from last week when you guys did research on all the planets, but then applying it again to exoplanets. Because if a planet has a really, really high mass, it probably has a really, really high surface gravity. If a planet's really, really close to its star, then it's going to have probably a really, really high temperature. And what a lot of you are probably finding out if you're doing application A are the easiest planets to find are really, really large planets really, really close to their sun. Because they cause a lot of wobbling with their sun, because there's a lot of gravity involved. And also they're very, very hot. So you can find them in the infrared wavelength. On an infrared telescope, yes, we have big, almost like thermal cameras acting as telescopes. Okay? Some things are easy to find at infrared than they are invisible. They give off more heat than they do visible light. Brown dwarfs are similar to that, those boundaries between planets and stars. So that's the DNA number 3. That ends DNAs. Your quiz is tomorrow. Okay? So I got an email, when is the DNA due? DNA sheet is due today before midnight, or as soon as you're done, turn it in. Look it over. I'll post notes today. Study. We'll review tomorrow morning. You'll take the DNAC tomorrow morning. Okay? Friday, there is no stream. You're working on things you haven't finished, like phase 2 today, or starting phase 3, or any other of the revisions you need to do. And there's also the mighty meetup on Friday, which a lot of us will be doing. All right? So I'm going to transition. Review of each app in the GSA. Make this a little bigger. Yeah, I'll be playing in categories. I like competition. We'll start with application A. We'll talk phase 2. So you only had to do, again, half of phase 2 for your application yesterday. You're going to finish up the second half today. So phase 2 should be done. congratulations. After today, half of your application should be all set. All right? But the harder part, phase 3, is coming up. Okay? So, getting there, but not quite. Evidence and data supports in building a well-written argument. You're trying to establish your point as the best possible avenue in a research-based approach. So you're developing your claim based on your research after this. Okay? Your direction is again to gather data on exoplanet habitability from at least 5 sources that provide accurate and reliable information. Use URLs, websites, and with .gov.org or .edu. This is very similar to application C. You're doing a lot of research, but you have to make sure it's accurate and reliable. Okay? Focus your research on tilt, distance, type of star, habitable zone, and mass. So I've seen 2 basic approaches to this application. I left it open-ended because I wanted you to take the track that would make you the strongest in making your best research-based approach. Okay? You can do one of these 2 ways. Okay? One way is not better than the other. All right? The first way I've seen is you literally take each of these categories or more and you just answer them with a source and then provide information from that source. There's 5 categories, there's 5 rows, taking care of what you need to get done. All right? Looking for a source for each of these. All right? So, that's one way to do it. It's very similar to how you would do tour of the solar system. It's almost like tour of the solar system was practice, huh? So, you are finding a source that answers one of these categories about the Earth and exoplanets in general. Okay? You're comparing the 2. And if you're doing it this way, then later on in phase 3, you're more arguing what the next habitable planet would need to have. You're arguing for the conditions. Okay? I've seen a second way on how this is done, all right, which I think is pretty cool. But you don't have to all of a sudden change what you're doing to do this. Okay? And that is, people are finding 5 different exoplanets. They're Googling and researching what are some possible habitable exoplanets based on Kepler data, the Kepler Space Telescope, and Hubble, and other observatories in space, satellites that have telescopes on them. And they are looking at 5 exoplanets and then providing their distance from the star, their habitable zone, the mass of the planet, how much water does it have, does the star produce enough heat. So they're analyzing 5 different planets. And so what's going to happen is in their CER, they're going to start arguing which planet would be the best place to try to make a human colony. So if you are just answering each of these categories with your own research, like tour of the solar system style, you'll start writing a CER that's going to be, what does the next planet, what does the next colony need? This is a checklist. Use this checklist to find out if you can settle on this planet. Okay? If you're researching 5 different exoplanets, you're going to eventually argue this planet is the one to choose. Kepler, whatever, whatever, whatever. Or Gliese, whatever, whatever, whatever. A lot of them are named Kepler or Gliese because of their instruments that were found used to discover them. They're not named after people, only that they're named after astronomers. That the telescopes are named after themselves. Okay? So that's application A. You are finishing your research today. Alright? If you are researching different exoplanets, you need to provide several of these categories for each of the planets. If you're just researching each of these categories, you just need one source and a couple bullets. That's it. Okay? Why can't humans just be happy on Earth? I am. Because for the most part, like I said, back on Monday, it kind of engages our imagination in science fiction slash fantasy, and humans have been explorers pushing the boundaries, because life tries to fill all niches almost, too. Gives us a direction and a purpose. Plus, we're kind of ruining this planet, and is there a second Earth? But then it also kind of goes against the argument, if we're ruining this planet, what says that we deserve a second one? So, it's boring, there isn't any new things anymore. But then, you'll be looking for planets that are most similar to Earth, though, Hayden. So you're just trading one location for another? That's pretty much the same. And I get your point, though. I'm just playing devil's advocate. Alright, application B. You guys are hands-on. You guys are trying to build a spectrometer. Something that can split light so that you can analyze and look at light. This is kind of like the blueprint. It's very weak. I pulled it from NASA's website. If you got stuck on directions, there was a video from the University of Oxford on how to make it. Different light sources produce different spectra, which are rainbows. And some light sources have black lines in them, which means they're absorbing that wavelength of light. There's molecules in the way between your eyes and the light source that are absorbing that light. And that's how you can identify stars. Okay? Certain elements and compounds take up bands on the rainbow. Alright? And when they absorb that light, you don't see it, but then you know that molecule is there. Alright? That's why we know that our star has a lot of actual oxygen on it and near it. To infinity and beyond. I like it, Kim. And so, if you are having questions on what a spectra is, watch Does the Sun Have a Shadow? This will help you write your analysis slash conclusion later on. Alright? Today you are doing testing, due on 4/29. Oh, today's 4/29. Okay? So, you need to find a ceiling light, use a flashlight, use sunlight from a window, and then find something else. I think something with a flame that is safe is something cool to do. Alright? A candle. I don't think any of you have a campfire right now. What else could you do if you were safe and can get a street light? Maybe use a street light because they use special bulbs. Energy efficient light bulbs versus old school light bulbs. The spirally light bulb versus the incandescent spherical light bulb. Checking out the spectra for that. You just got to differentiate what light is for your ceiling light and then what light bulb you're using as an extra one. You're going to provide the colors and then an image of the spectra. You can either take a picture or you can draw it in Google Draw. Alright? So let me just provide an example to you to kind of help you. Alright? There's my camera. Oops. This one's mine. Right? Viewing hole. CD at a roughly 60 degree angle. I didn't tape it up on the sides right now. And then the hole where you allow light to come in. I followed the University of Oxford's tip in that aluminum foil is easy to cut. And it makes a very sharp cut. You want this slit to be as thin as possible and then as clean as possible, because you want a very thin band of light to enter in and then refract on the CD as a spectrometer. Okay, so this morning, some bright sunlight instead of dark gloom. This is the picture I have. Okay. Notice that you have a rainbow. Violet down to red. Okay? So you can take a picture or you can draw it in Google Draw. And then you would go back here and you'd insert the picture or draw. What do I mean by Google Draw? Insert image. No, drawing, new. There we go. And I'm not going to make it perfect. I mean, I could like make it like a little trapezoid and whatever. But I can make maybe a series of rectangles. Put them next to each other. Obviously purple is kind of small, so violet, I make that a little smaller. What else? Blue is larger, green. So then I just fill it in. Violet, blue, green. Alright. And I can just keep building. I can save and close. Come on. What's going on here? My drawing decided to go off screen and go rogue. Hopefully it doesn't happen to you. How do you get an exact 6-degree angle? Well, hopefully it's not 6 degree. Hopefully it's more like 60 degrees. Nikolai. I did an estimation. So it has my original pit. Okay, save and close. Put my picture in there. Was it being blocked? What's going on here? I don't know, maybe the comet's messing it up. Hopefully you don't run into this issue. You shouldn't be. We've done drawings plenty of times before. Alright, so you just make your drawing or take a picture and put it in there. Maybe crop it a little bit. Like you don't need all this extra. You double click your picture and then you can move the black bars in and you can crop it. Okay? Like I was saying, Nikolai, you have to estimate. So estimate at a 45-degree angle. Obviously 45 being halfway between a 90, a right angle, and then just tilt it a little further, a little more vertical. So it's a little more vertical than a 45-degree angle. So from here to there. So you got to estimate. You got a protractor at home, go right ahead and use it, but I didn't make that one of the required materials. Okay? So my picture, my drawing's in there. Colors with major absorption. Again, you're looking for black lines. You're looking for black lines. This right here is not an absorption line. This is just an artifact on the CD. Maybe like a scratch or something. I don't see any clear black lines. I mean, it gets darker because there's just less light as you move along. The only place I can really see a black line might be somewhere in the low green wavelength. And so I would say almost none, maybe one in the low wavelength of green. Okay? And so I'm just kind of giving a description. Hopefully you see black lines in some of these others. Remember, the sun makes light, and if it's going to make light pretty much across the spectrum. So you shouldn't see black lines really in the sunlight, but if you see something, try and make it out. That's kind of reaching. I mean, I'm using this as an example. For the most part, I would say, now this is pretty much clearly no colors have absorption. Okay? Any questions on application A or application B? I had a couple questions yesterday through Remind on C. One, well, also one through email. One was, I'm having trouble finding information. Well, I would start by just Googling interstellar travel NASA. And then there's a PDF on the second hit. That's kind of like a little slideshow. It's an old NASA PowerPoint. And if you kind of scroll down, they start getting into how chemical rockets can't get us to the stars. Fission doesn't have enough energy. Fusion could be one possible solution. There are some starship designs, like the Daedalus, or using antimatter instead of fusion, because mass can become energy and energy can become mass. That's Einstein's equation. Using antimatter, matter with opposite charges, completely annihilates other matter and creates 100% energy. Okay? Chemical rockets are very, very inefficient compared to something like antimatter. You need 100 to 1,000 tons to reach the Centauri system, which very hard to do. You can make just atoms of it in a collider. See, $100 trillion per gram. And then there's something like a long-term solar sail using photonic pressure, light pressure. Light can generate pressure. And then maybe using something like NASA's Breakthrough Starshot, which is a little chip, but it has a solar sail on it. And it may take several years to get to its destination, but it'll eventually get there and be able to record information. So that's a good source to start. And so I would then go on to then Googling Breakthrough Starshot. I would Google fusion propulsion. I would Google antimatter drive, okay? Or Google on your own, like NASA warp drive. Like in Star Trek. Is warp drive real? Has NASA really created a warp drive? Scientists are starting to take warp drive seriously. What? So you go to nasa.gov and you can kind of pull some information about warp drives. Warping space. That's what we're going to talk about when we talk about gravity. Mass can warp space. I can't find anything on how communications would work. Unless you have some kind of subspace communication, your communications would be lagged by light years. So maybe that's one hurdle you came up with, Hayden, that hasn't been addressed. So, light year communication. I don't know about this source, but how could we communicate over light years? Let's take a look at this source. It's like a Yahoo answer. So there is lag. I don't think you can really get around unless you can think of some kind of, again, subspace communication. You just kind of go back to how things used to be. Instead of instant communication, like you'd have to wait for a letter to be delivered. In the Middle Ages, that could take weeks, if not months, if you even knew how to write a letter in the Middle Ages. So we're talking like 1800s, 1700s. So if that's a hurdle, I would still make it as part of your solution. Later on down the road, when we start to get to phase 3. So you're gathering data, you're gathering your solution, the title. So fusion propulsion. You start typing information about the fusion propulsion, give the source with it. Okay? The data list design, maybe breakthrough starshot, warp drives, things like that. Okay? And so another follow-up question was over remind is, am I looking for solutions to the problems I came up with in the first question? Like what challenges exist? I said no. You're not looking for specific solutions to your specific problems. You're looking for all solutions that you can. Because at this point in your brainstorming, no solution is a bad solution. What you're going to do is you're going to eventually do your due diligence down in part 3. You're going to see which solutions matched your problems the best. And then you're going to give me 2 designs and their explanation on how they address your problems. Okay? So that's tomorrow, getting started on that tomorrow. If you're in App C, engineering your own spacecraft, you're just looking for all possible solutions. All right? Finishing up this chart. So that's all you have to do is phase 2, your table for phase 2. Again, if you're not doing the table, delete the table and get it out of there. If I'm doing app A, delete this one, delete that one, leave the red table there. If I'm doing app C, get rid of the red one, get rid of the blue one, only have the purple one. So you end up customizing your assignment. All right? How do you delete a table? 2-finger click anywhere on the table, and there will be a delete table. Okay? Any questions now? I had one pop up for app B. Will the absorption line be going across the colors or with the colors? So it was asking, will the absorption line go horizontal or will it go vertical? The absorption line should be going vertical. Okay? This right here, this line, this brighter line is not an absorption line. Absorption lines should be going vertical in the color that they're in. They should not be going across all colors. Okay? If you guys have questions throughout the day, let me know. I'll do my best to get back to you as quick as I can. Help get you done through phase 2. That's all you need to do is phase 2. You don't need to do more. We'll work on starting phase 3 tomorrow. We'll not finish phase 3. We're going to start phase 3. Tomorrow we will review for the DNAC, take the DNAC, and start phase 3. Make sure you turn in your DNA sheet before midnight for a little extra point. Turn it in as soon as you're done. I'll be taking a look at them as you turn them in. Alright? And then one last note. Friday is our big mighty meetup. Had some trash talking already in categories. Perfect. I love it. Double the pride, double the fall. But remember, Halman's got his puzzles. We have drawing in the studio with Miss Grant. And then in the theater, Miss Kilda finally settled on Onward. She came out early on Disney Plus. She's going to be trying to figure out how to get Disney Plus to stream, well, not stream, but to pop up in a Zoom. Alright? Remember, we will all be in the same meeting to start, and then you'll be placed in those little side rooms. Alright? So still be in the same meeting all the time. Just there's little rooms you can be put in a Zoom meeting. A little better than Meet. Meet, you're kind of just all in the same place all the time. Alright? I will catch you guys tomorrow. Have a good Wednesday. Bye, Hike. Bye, Ryan. Bye, Hayden.